Hi there and welcome everyone to the first video in chapter 11 of the DB2 course. You know that I never grow tired of reminding you that the relational data model is an unsorted data model, so there is no defined order on the rows inside a table. But what this chapter is going to talk about is exactly the establishing of order, the sorting, and then also later on the grouping of the rows inside a column. And as we will see, this is not only relevant when we add an order by clause to our SQL queries. Sorting pops up all the time in all kinds of situations. You will find sort operators of various flavors inside the query plans. And because sorting is so ubiquitous, it makes sense to have a closer look at how sorting is indeed implemented in such a database system. Sorting may add a substantial share of time to the execution time of our query plans, and it makes sense to understand why that is and what happens behind the scenes. And this is exactly on the table in this particular chapter 11. All right. So without further ado, let's get into that. Let's first remind ourselves what a central role, how important sorting can be in the evaluation of relational queries, of SQL queries. Okay, and for that, actually, we could pick a lot of queries that show that sorting plays a central role in query evaluation. So what I've decided here is, if a single query is not enough to study the impact and the role of sorting, well then let's study a whole family of queries. A whole family of queries, Q9 of probe queries, that will lead us to very similar observations that sorting is pivotal in the efficient execution of query plans. All right, so here's a selection of queries, and there is many more that would lead to sorting in query plans. They are all formulated over the indexed table, which is the table that we've studied while we were talking about B+ tree indexes. And currently we assume that there is a single index, a B+ tree index defined. A sorted index is defined on the A column of our index table. I will remind you of the definition of the index table when we switch over to the PostgreSQL terminal in a second. All right, so this is the first query that I would study in this context, and well, it features an explicit order by clause, and you would expect sorting to play a role in the evaluation of this query. And of course, you are right in expecting that. Well, we will see later that a slight change to this query already leads to indexed usage, but in general, well, we will be relying on the evaluation of sorting as we evaluate the plan. All right. The same happens when we look at this particular query. There is no order by clause in this query, but we are looking for distinct C values in the index table. And well, there's many ways in which you can evaluate such a distinct clause, but one way indeed is sorting. If we sort the rows of table indexed in C order, then all the rows with equivalent or equal C values will be adjacent after the sorting has been performed. And well, from this sorted representation of C values, it's easy to pick and identify the distinct C values. All right, because, well, equivalent C values will be adjacent to each other. Right, so sorting can play a role in the evaluation of distinct. Sorting can also play a role in the evaluation of group by. Again, we are interested in bringing together those rows of the index table that are indistinguishable regarding their C values. If all the C values are the same, then we have found the rows that belong to one group regarding the C column. And well, if we found that, if we have all these rows adjacent to each other, then it's easy to evaluate such a group by clause, and also easy to evaluate this summation here, right? So in performing summation inside the group is easy once all the rows that belong to a group are physically close to each other, and sorting will deliver just that. It might be not so apparent where sorting comes in when it comes to the relation of such join queries. You see, this is a self-join query, but that this is a self-join is not really that relevant to our discussion. It's the only table that we are currently looking at, the index table. So to perform a join, let's perform a self-join between the rows of the index table themselves. And you see that we are using this equality condition on the A and C columns to identify the join partners. In such situations, there's an opportunity to sort the rows in the participating tables. In this case, to sort the rows of the index table in the A order, and to sort the rows of the other index table in the C order. And once we've done that, we can use a particular algorithm called the merge join, sometimes also called the sort merge join, to really make the point explicit, to have a very efficient evaluation of this join condition and a very efficient way to find those rows that contribute to the select clause here, to the result of the query. We will talk about these various forms of join algorithms, and sort merge join would be one such algorithm in the upcoming chapter. Okay, so let's see whether we indeed find these sort plan operators in all of these scenarios over if we switch to PostgreSQL. And there we are. So that would be the PostgreSQL terminal, in which I've already prepared the creation and also the instantiation of our index table. So this is just to remind you of the definition of the schema of the index table. All right. As you have seen in all of your queries, we are sorting regarding the C column. So the C column has been this numeric column, no index on the C column. We have a single index on our primary key column A here. You see that I've already renamed the index to be named indexed_A. I have loaded 1 million rows, as we have done before. I've analyzed the whole thing, and what I end up with is this particular situation. Okay, so the index table with 3 columns and a single B tree index on the A column. All right. So now let's have a closer look at the plans that are generated for the 4 queries of the family of Q9 probe queries. To really have the focus on sorting here, we will temporarily forbid PostgreSQL to use hashing to execute these queries. Our focus is on sorting now. There is always the possibility to instead of sorting, to use hashing during the evaluation of these plans, and hashing will pop up when we talk about the join algorithms in the next chapter. But for now, our focus is on sorting, so let's disable hashing for the moment. Okay, so let's look at the first query, the obvious order by query, which should include a sort operator when we look at the plan. So let's look at the plan and see what we find there. Okay, it takes some time, 1 million rows, they have to be sorted. All right, so this is the plan, and indeed there's not much happening here. Actually, the sort makes for the entire plan. The sort would be the root operator of this particular plan. This query does not do much else beyond sorting. Okay, so you see that we are sequentially scanning the rows of the index table, which of course is not ordered according to the C column. All of these rows then flow into this sort operator. Okay, the sort operator has a sorting key, a sorting criterion, which would be the C column here. That's expected. Okay, so this matches our order by sorting criterion here. And we also see that a particular algorithm has been employed to perform the sorting. It's the external merge sort algorithm that has been employed here. And we will have a closer look at how external merge sort functions in the upcoming videos. There is disk space usage involved here. The external merge sort already hints at the fact that sorting indeed happens with the help of the use of external, so non-RAM memory. And indeed, we use disk space to perform the sorting, to hold temporary data structures that we need during the sorting. All right. Of course, such a sort algorithm would not be as efficient as a purely in-memory sort algorithm, but well, since we have ample temporary disk space available to perform sorting, we would expect this particular sorting operator to be able to cope with really huge inputs that need to be sorted. There's one other thing I would like to point out, and it's related to this particular value here. Right, so the actual time value you've seen in the in all of the plans, in all explain analyze plans, we are also seeing reports about the actual time usage that one plan operator has contributed to the overall execution time. And if we look at the actual time that is being reported for the sort operator, we see two time values. These are actually measured in milliseconds. So we see this first time value and then this second time value. We will have a closer look at these times when we talk about plan evaluation and the orchestration of operators. But let me tell you that this first time measurement means that this is the waiting time that we had to endure until the first row of the output has been produced. Okay, this is the time once that we have to wait until the complete output has been produced. All right, so before we see the first row in the output, there's actually a waiting time of 3.4 seconds. Once we've endured that, then well, the rest of the result is produced in the time frame of 1 additional second here. And well, of course, there's waiting time because we have to perform the actual sorting, the external merge sorting, before we know what will be the row with the minimal C value in sort order. And only once this row has been found, we can actually start emitting all the results. So there is some blocking here, some latency, some waiting time that we have to accept when we do sorting before the first row can actually be seen. So this is the consequence of, well, the fact that we have to use an explicit sort operator in the plan here. All right, so let's look at the second query, at this distinct query that looks for distinct C values. All right, so this is the plan. Let's look, well, there's of course the scan of the rows of the index table, and they again flow into an external merge sort that indeed again uses external disk space to perform its work. The sort key again is the C column. Well, of course we would order the rows in C order so that adjacent C values are adjacent to each other, and so that we can easily identify the distinct C values. If you compare the disk space here, which is 14,696 kilobytes, it's less than the 50,976 kilobytes above here. This is due to a very intelligent and clever treatment of duplicates that is built into the sort operator that is already comes into play while we are sorting. So this particular sort operator knows that it's not supposed to produce duplicate values, and during sorting stuff is already thrown away. So we can get away with less space usage here. Nice. All right. So now group by the grouping criterion C, which again will lead to a sorting by column C. Let's look at that. All right. Okay, stuff. Okay, well, there is the scan of the rows of index E and index I, and this is the sort again regarding our sorting criterion C here. All right. Well, that's it. Well, disk space usage is a bit higher now because Well, duplicates have to be taken into account here, but we may throw away the B column, the textual B column. This already saves some space when we create the sorting output here. Okay, but again, sorting takes the central stage here of this group by plan. Okay, indeed, the actual grouping, let me scroll to the top here, the actual grouping performs after we have done the sorting. So this group aggregate will then indeed detect the group boundaries inside the sorted rows of the index table, and then will also perform the summation. We will have a closer look at how grouping is evaluated in later videos in this particular chapter 11. All right, and then there's the merge join, the self join between the rows of the index table that is based on this equality condition. And joins with such equality conditions can be evaluated using the sort merge join algorithm. Let's have a look. Okay, so let's scroll to the middle of the plan where we will indeed find the merge join algorithm. So indeed the core of the plan in this case is the join operation, which indeed takes care of all of this part of the SQL query. The unique on top here then is only some post-processing that will take care of the distinct semantics. Right, but the merge join takes the center stage here. And the merge join has two inputs. You would expect that because, of course, two tables contribute rows to the computation of the join. All right. Well, we see the join condition here, the join predicate, but below that we indeed see that two row sources contribute the rows to the merge join. One such row source would be the indexed A index. Okay, we can even use the index only scan here because knowing the A values of the index rows is enough to evaluate this predicate, and it's enough to indeed evaluate the select clause here. So an index only scan is sufficient. This will produce the rows in A order. All right. Below here we find the second source of input. It's indeed a sort operator plus some additional materialization. Let's not look at that here. It's a sort operator that will also scan the index table, but will produce rows in C order. Okay. It will produce in C order. So rows will be flowing into the merge join operator in A order and in C order. This is the requirement that merge join has to efficiently compute this join result and find join partners. We will look at merge join more closely later on. Okay, right, and then there is a fifth query even here in this buffer, a fifth query that's not mentioned on the slide, but well, this query is using a window function whose semantics is also based on an ordering of the rows of the underlying table. In this case, again, it would be an ordering regarding the C column. And if we read this query, then we will see again sorting will play a central role here. Wait a few seconds. This is the result of our window query. Again, it's a sorting query. All right, and some window aggregation on top of that. So indeed sorting is ubiquitous in the evaluation of a large family of SQL queries. All right, so sorting takes its time. So we have just seen when I evaluated these queries, there was some waiting time involved, like 4 to 7 seconds is something that was typical for this experiment. Indeed, sorting takes its time, and it's one of the more costly operators that a relational database system will evaluate or will encounter during plan execution. Of course, the system will try to be clever and try to avoid the use of sorting altogether if this is possible at all. If the system can in any way rely on rows that are flowing in to an operator, can rely on these rows to be sorted already, then sorting will be omitted if this is possible at all. In the queries that we have just looked at, there is the there's this sorting criterion I.C that occurred all the time. If we would replace the sorting criterion by I.A, so we would only very minimally edit the queries, you will see them edited in the buffer in a second. If we minimally edit this query and switch from the C-based to the A column-based sorting, well, then there's the opportunity to use the index, the A index, the B plus tree index, which is indeed sorted on the A values, to use that index in place of the explicit sorting. Sometimes we may even use the index only variant of the index scan and be even cheaper in this particular in these particular cases. So if sorting can be avoided at all, the system will indeed try to do that. Let's quickly switch over to the terminal once more and see how this is indeed happening. So what we see below here is a selection of the queries that we've just seen. I've only switched the sorting criteria or the grouping criteria or the distinct values criteria from column C to column A. Okay, so if we look at this query one again, then you see that the evaluation time is lower here. And indeed, if you look at the plan, well, this is indeed a sorting-less plan, a sort-less plan. We can evaluate this plan by simply performing an index scan on the indexed A column, right? On the index A index, I'm sorry about that. And well, its order of entries in its sequence set coincides with this order by criterion. We have discussed this when we talked about how B plus trees can support queries other than selection or queries. And in this way, sorting can be avoided. And what you will also see is, if you have a look at this actual time output here, and if you recall that this first time here is the time that we have to wait until the until the first row of the result can be seen, then it's a completely different situation if compared to the explicit sort. Since the index is already sorted in A order, we can simply start our index scan from the very left of the sequence set and immediately start to emit rows. There is no latency and no waiting time involved. The first row will appear immediately after the query has started. So that's completely different behavior if we compare this to the explicit sort. Yet another reason for the system to prefer index scanning: reduced latency, reduced waiting time. Okay, so I think the picture will be very similar in this distinct case. I think we should see an index only scan in this particular situation, because A is all we interested in the final result. So there you go, it's an index only scan, right? And again, no waiting time involved here, right? Okay. And then this last query, it's a group by query. A group by query that now uses the A column as the grouping criterion. We could scan the sequence set, we would encounter rows in A order. All rows that belong to a single group would be encountered in adjacent fashion, would be next to each other already in our scan of the sequence set. Finding group boundaries in such a setup is very simple, no sorting involved here. Well, at least hope so, otherwise my experiment goes wrong. All right, so it's an index scan on the index A column. All right. Right, the grouping key, so which criterion will be used to find the group boundaries, is indeed the A column. It's very simple to do this grouping on A ordered output already, and we could immediately emit the grouping result here, which of course uses summation on the C column now. All right, so this is how the system tries to avoid sorting, because as we will also see in the further discussion in these videos, sorting can be time intensive and it can also be space intensive. let's re-enable hashing here. Okay. So back to the slides here. So we've just made this point in the experiment. We have already talked about this observation that explicit sorting can lead to latency that we can avoid if there is index support available. This point we've already made. There is some waiting time before the first row can be seen in the output. Once we have we have endured this waiting time, the rest of the output can be produced in a quick succession. But before we can emit the minimal row in sorting order, there is some waiting time. All right. So sorting takes time, but sorting also needs space, right? So sorting may need temporary working memory, and maybe it needs lots of temporary working memory. So the system will make a prediction about the size of the working memory that is needed when it performs the planning, right? And of course, the system will try to stay RAM resident if possible. So try to avoid the use of external disk-based memory to save temporary sorting results, so partially sorted relations. All of this would lead to additional disk I/O, moving temporary results out to the disk, and then later read these temporary results again from disk into RAM to perform further stages of sorting. All of this will be described in further videos, but all of this, of course, needs time. It needs I/O time, and it needs space on the external disk medium, right? So only if we have really huge temporary working memory requirements, or if the working memory is indeed scarce, only then the system will choose to perform external sorting on the disk. And so if you look at query plans that feature sort operators, then of course you will see such a sort operator in the plans, but you will also see additional information about how these sorts have been performed. In-memory sorts will be performed using the regular quick sort algorithm that you probably know. And this is the non-disk variant of the sort execution that we should aim for. If this is not possible, we will see an external sort or an external merge, as it's called in the plans, and we will also have a measure of the disk space that will be used to perform these external sorting algorithms. What you will also see, if you also output the buffer information for these plans, that there will be additional reads and writes to buffers when we perform these external sorting operations. This is expected because there will be additional disk I/O. All of this, of course, will slow down the plans. So before we close this video, let's switch one more time to the terminal. There we go. And let's see how PostgreSQL chooses between the disk-based and the RAM resident versions and variants of its internal sorting algorithms. So let's first look at the available working memory that is currently configured in our instance here of PostgreSQL. I think it's the default of 4 megabytes. Okay, so 4 megabytes is really scarce if you are dealing with large relations. And indeed, as we have seen before, if we try to sort the indexed relation using an explicit sort by the C column, then indeed we will see that the external disk-based sort algorithm is the choice of execution here. Execution method, yeah, indeed. So we sort by the C column, but we need the external merge operator that uses disk space, and indeed it performs quite some I/O here. Actually, it appears that all of the pages of the underlying relation have been written and then read back in. And we will see that this is indeed the case once we look at the details of this external merge sort algorithm. Okay, if we now increase the available working memory, which would be a much more reasonable value for a system like this, which I think has 16 gigabytes of RAM. So let's invest some gigabytes, 1 gigabyte for example, for working memory here. Then we will be rewarded by this investment. If we perform the same query again, we will see that the sort operator will resort to an internal quicksort. All right. So indeed, quicksort, no external merge sort here, no disk involvement, no further disk I/O that is being reported here. But of course, we needed our share of memory here, like 100 megabytes. 100 megabytes were needed to sort the rows of the index table in C order. All right, but working memory was sufficient to hold that. Right. So we will look at how external merge sort works in the upcoming videos. You probably already know how quicksort works. It's a rather standard quicksort implementation inside PostgreSQL, one that can deal with duplicates in an efficient manner and can throw duplicates away quickly, as we've already discussed. But otherwise, it's normal quicksort. So our focus in the next videos will be on the external merge sort. So let's switch back to scarce working memory. External merge sort will be used now. To see how this works internally, I invite you to look at the next video. See you then. Bye bye.